I sat there for 35 minutes trying to remember. I think it's not how to do this. I was like, I was trying to turn the triangle into a 90 right triangle.
I didn't realize it was
Not a bad idea. One of the side lengths was square root. It gives me 666. Yeah, that's not great.
W22.
Subspaces. Too bad. It's like substance. So it's like,
Yeah.
Good, how are you?
struggle that I'm so I had all of this
You seem very. I wonder if you
needed to study them.
art.
Entirely new types of math, linear algebra,
I
and
went in thinking that I was gonna. I don't think I did.
introduction.
But I don't know if I did good.
I have to actually study it.
Did I squeeze in?
I really
I actually went in thinking I would do okay, and then I.
the good news is on the other math class, I got 90.
Oh, there you go.
What was saying right here?
That's actually easy.
Did not do well. I genuinely think that's it.
Yeah, staying up late.
The email trail? About your grades do not.
Homework for today, right?
I forgot.
Me neither, but I started reading the comic, so it'll be a little left that one. Issue number 30.
I saw if the equation lined up with that point.
Close now.
How's everybody?
Good, how you doing?
Doing well.
You watch Super Bowl?
I did not watch the Super Bowl.
Pretty good. Nice.
We have better things to do with our family and family. I'm not judging. None of my kids who knew who were playing in the Super Bowl. Like this last week, we started something in our family where after dinner, all the phones go in a basket. And so there's no phone or go. You can hop up and go and check tasks. And then you can back in. You have to like scan the task. And it's not a lot. Getting more people involved in it. Yesterday we had mandatory game pretty much. We played sardines. Do you guys know what sardines is?
Yes,
We have we turn off all the lights in the house and you have one person. And then everyone else has to go find the first. If you find them, just try to hide. I'm too big to find any good hiding spots, so I just help the younger kids. It was really my youngest one is 8. But we've done some pretty crazy things. Pulling the drawers out of the a set of drawers behind the drawer. They were already digging out partially. It's like you pull them out and hide them way behind the drawer. So when they weren't very big, and then you put the drawers back in, you know, partially, so they're sticking out. They fill the space. So, yeah, some good stuff. Okay, I'd like to start us off with a prayer. Thank you.
Father in heaven, we are grateful for this new week which we have. We're grateful that we could be gathered together in a place of learning, and we ask for thy spirit to attend with us. We also pray that we'll be able to see the people around us and know who we can serve and how we can best serve them. And we ask for this in the name of Jesus Christ. Amen.
Are there any BYU connections in this Super Bowl? I know there were at least 4 Utah connections. I just saw the I saw a headline that said there were 4 Utah connections, but I know one. I only know one of them. So there's a former UVU soccer player. He loved soccer like crazy, and I think he was like the leading scorer in the WAC or something. And this coaches, if I remember right, his coaches at UVU said you need to lose some weight. He was pretty heavy. He didn't look like a soccer player. He was a pretty heavy set guy, and you need to lose some weight, or you know, they're not going to have you playing on the team. So he gave up soccer, and he started playing football. He kicked for the University of Utah. His name's Matt Gay, and he kicked a field goal for the Rams, and he has a Super Bowl ring. All because his coaches at UVU wouldn't let him play in his preferred. So good for him. So it may not have seemed like a blessing at the time, but he's probably in a better situation. All right, here's a couple things to think about related to subspaces. Big new topic. We're going to spend 3 days on this section. There's a lot in this section. We're going to be pulling together a lot. The main ideas are not far removed from stuff we're already doing. We're putting some new language on it and some formal mathematics around it. And it's probably pretty confusing for you right now. Some of it's a little abstract. The abstract is very powerful, but can also be hard to work. You're like, why are we doing this stuff? So, so take a minute, think about these things. The key on the second one, we're thinking about the idea of closed. A big idea of subspaces. Subspaces are closed under certain operations. They're closed under addition. They're closed under scalar multiplication. Closed meaning if you take 2 things in the space and you add them together, then you still end up with something in the space. Or if you have a vector in the space and you multiply it by a scalar, then you're still going to end up in the space. So that's what it means to be closed. Like you can't get out of it just by doing an operation. So here's a way for you to think about with something you're more familiar with, some number systems that are and about whether they're closed under certain operations. So go ahead and think about those for a couple minutes, and then you start talking to your neighbors. Okay.
Well. Do it first. Set it. Subspace is just like from what I understand, it's a subset of
Powers.
and of is a subset of where integers is the same thing. And vector and standard position quadrant is obviously. Then it's also in the other subspace of that first quadrant of the square expression.
They are still in
Subspaces.
because there's an uncounted integer, whereas if they were finite, then it wouldn't be an infinite.
And then it's like number like finite.
So I think
I was like,
you can also make an infinite number of subsets with a finite number of elements. Since that a lot of them are going to look the same. Just by technical numbers. They are, aren't they?
Actually, fraction powers.
Oh, yeah.
The what happens.
They're not closed under any of those.
Yours is. Oh, yeah.
But not subtract and division powers. And they're closed under addition. So addition and multiplication, they're closed.
Yours are two.
Let's talk about this first one.
It's also shows it
Go ahead,
with
finish
me on
it.
the testing center, but
Right. Are vectors in standard position? Someone asked me about standard position, so just a reminder, a vector in standard position means it starts at the origin. Okay, so vectors refer. It's usually easier to think about vectors referring to movement rather than a position. So, but if I write down the vector 2, 1, then if I put it in standard position, then that points to the point 2, 1. So, but the vector 2, 1 can think about moving anything 2 in the x direction, 1 in the y direction. So you can think about it as movement or change or a force in that direction as well as a point. But the point refers to, if you do the point, then you start the tail at the origin. Okay, so we have vectors in standard position in the first quadrant, a subspace of R2. So if it's in the first quadrant, then both x and y have to be larger than or equal to 0. So the question is this a subspace or not, and why or why not? So if you think it's a subspace, you can do a thumbs up. If you think it's not a subspace, thumbs down. If you have no idea, you can do thumbs sideways. Okay. So go ahead and show me your thumbs. Okay. Lots of thumbs up. Couple thumbs sideways. Not very many thumbs down. Okay. Why thumbs down?
It's not subspace,
Why?
because if you subtract 1 minus 2, you're going to get negative numbers, and that's not in a whole number area.
1 minus 2. I have a vector, so let's say let's do 1, 1 minus 2, 2.
Sure.
Okay, so is 1, 1 in, is that in that first quadrant?
Correct.
In standard position? Yep, so that's in that part. How about 2, 2?
Also good.
Also good.
It's actually
If we
double-
add these together, are they in there?
yeah, 3, 3.
Yeah, so 3, 3. Like, oh, that's good. So it looks like addition, we're okay. What about scalar multiplication? I have 1, 1, and I multiply it times 5, I get 5, 5. Isn't that in there? Yep, or I should, maybe I could even do like 1, 2 times 5, and I get 5, 10. So I haven't run into any problems yet. Negative, right. So what if I do a negative, just a negative 1 times 1, 1? Is it -1, -1 in this first quadrant? No. So it's not closed under scalar multiplication, because if I multiply by a negative value, I could end up out of it. And then if it is closed under addition, if I just take two of the two values that are in there and two vectors and add them together, I still end up in that first quadrant, but not here.
Fraction and division is where it has issues.
Yeah, right, but the subspace, we only have to worry about linear combinations. We don't divide. We just have to worry about scalar by a real number, scalar multiplication, and addition. Yeah, but for our subspace, we only have to worry about those numbers.
So were you saying that the subspace is the first quadrant, or were you saying that the vector originally is it?
So the question is all of the vectors that are in the first quadrant, are they a subspace? Meaning, there were 3 criteria that you read about, and we talked about in the video, that you have to have for a subspace. It has to have the 0 vector. Technically, it just has to be non-empty, but the book just says it has to have the 0 vector. It has to be closed under addition. So 2 things in there, when you add together, you still have to end up in there. So that is right. If I take an x1 and an x2 that are both positive and add them together, I'm still going to get something positive or positive 0. Same thing with my y. So if I take something that's a y that's 0 or greater and a y that's 0 and greater and add them together, I'm going to get another value that's 0 here. So this is closed under addition. And the last one has to be closed under scalar multiplication. And meaning I can, if I stretch that vector, if I scale it and extend it, any real value, then it also has. But that doesn't work in this case. Right, because here I have the first quadrant. I can have a vector like this, but if I scale it this way, and it over there, I'm out of that first quadrant. So it's not closed under scalar multiplication.
Considering the first quadrant to be a subspace.
That's right. Like, yeah, like all of these vectors with these restrictions, is that a subspace? So no, because I can still, if I can do a scalar multiplication of something in there and then not.
But isn't it asking if it's a subspace of R squared?
No, it just means like it does live in 2. This is part of R2, but it's not asking if R2 is the subspace. This is just asking if this if the vectors in standard position that point to some point in this first quadrant, if that's a subspace. So if that subset of vectors in R2 is a subspace.
But doesn't R2 include just the whole plane of
R2 does, but the question is, so
You have to be able to form something that is in that form in order for it to be part of the subspace.
yeah, so
And
that's
since
just,
the negatives aren't in there.
it doesn't ask about all of R2, it just asks for the first quadrant. Those are in standard position that are in the first quadrant. Those are the vectors I'm talking about.
Answer should be in there. It was a subspace.
Yeah, if it was a subspace, then no, anytime I took 2 vectors in the standard position in the first quadrant and added them, I'd still get something in the first quadrant. And if I multiplied by any scalar, I would still end up in the first quadrant, but I don't on the scalar. Questions, Beth?
Is there any way to set a vector that describes the subspace of the first quadrant?
Nope. So the only way you can chop up R2 into a subspace is a line. So any line through the origin is a subspace, or the origin itself. It's technically a subspace. It's a really boring subspace. You just have only one element in the whole space. So yeah, that's the only way to chop up R2. So and it's one of the big theorems in this section is that the span of a set of vectors is a subspace, and any subspace can be written as the span of a set of vectors. And we're already familiar with spans of vectors. What do spans of vectors look like? They look like lines. They look like planes. They look like R3. They look like hyperplanes. So those are all of the vector subspaces we can get. The things that look like that. It might be a 2-dimensional plane in R5, some 2-dimensional slice in R5. That might be our subspace, but it's still a plane that would look or act a lot like R2. Good question. Other questions?
You changed it so it's.
What do you guys think?
Be additive. You could have
1, 2, and like -2, -1, and then.
I like your thinking. You're like, well, hey, we can, if I multiply any of these by a negative value, I'm only going to end up in the third quadrant. So maybe I can add that much and maybe it'll be okay. And the problem then is the addition part. And so, yeah, because then we could get, I could add this one to that one and that one or something. Yeah. I like your thinking. I like it. Okay. Let's talk. I'm going to talk a little bit about subspaces, and then we'll come back to that other problem. So, the idea of a subspace, the more abstract version of a span of vectors, as I mentioned before. Span of a set of vectors always makes a subspace, and any subspace can be written as a sum of vectors, even if the subspace is sound waves or polynomials or other things that are not like our vectors that we use. It turns out, like, to solve the cell phone problem of you're talking on your cell phone and you have to take that sound and compress it and then send it some way and then have them uncompress it. It turns out that's there's a way to think about that as a subspace, and with the ideas that we'll build up to, building a basis for that subspace in here makes it so you can compress that sound a lot and still have a really high quality. So, we'll get to that. The subspace has a property that is non-empty. So there are three things. It's non-empty, it's closed under linear combinations. Oh, that combines two of them. So it's non-empty and it's closed under linear combinations, but linear combinations can be scalar multiples and they're additive, or you combine them with some of this, a scalar multiple of this one and a scalar multiple of this one, and you add them. So must include the zero. This is what the book says, but it really is just an easy way to show that it's non-empty and all subspaces containing zero vector. So yeah, technically you just have to have it non-empty, because if it's non-empty and it's closed under the other two things, then you can just add the negative, the vector that you have in there. You just add a negative version of that vector, and then you'll get the zero. So cancel each other out. So zero is always. Yeah, or you can scale it by zero. Yeah. That's easier. The other two criteria is if U and V are an S, then U plus V is an S, and if U is an S, then C times V is an S. So those are the two added addition scalar multiple combinations. Almost all the subspaces we focus on are the subspaces of RK related to the kind of vectors we've been studying already. The columns or rows or the. So you can think about subspaces as a point, which we already mentioned, a line through the origin, a plane through the origin, a hyperplane through the origin. They all have to be through the origin because they all have to contain that zero vector. Okay. So I'm going to throw this out. This is big picture stuff. There are four subspaces to of a matrix. Okay. We have the row space and the column space, the null space, and the null space of A transpose. The row space and the null space tell us something about the inputs. These tell us about the input space. And when I say inputs, we're thinking about A times X. AX equals B. We're thinking about this X. This X lives over here in the input space. And B, that's an outcome. That lives over here. And in the column space, so we think about these, we can think about this as a function, and we think about this as the domain, and that's the range. Okay, so all of our inputs and our outputs. So think about this. So here I have a 2x4 matrix. I multiply that by, if I'm going to multiply by a vector, left multiplication, I multiply by a 4x1. Where does this live?
The fourth dimension.
It lives in R4. Okay. But the thing I'm getting out is just a 2x1 that lives in R2. right? So my row space and my null space of A, they're going to chop up R4 for us. This input space. I have to have four elements here so I can do the multiplication work out. The null space is all of the vectors. It's all of the vectors in this case R4 that I could multiply this matrix by and go to 0. Okay? That's why null is 0. Multiply it, it goes to 0. The row space is everything that doesn't go to 0, pretty much. We'll talk more in detail about the relationship between null space and null space later. The column space over here tells us where our outputs are. Let me go back for just a second. So my output, the most I could span is R2, right? Over here. If this was a rank 2 matrix, which it is, then I could get any point in R2. Okay. So my output spans R2. My column space would be all of R2. The row space would be a 2-dimensional span through R4. And that 2-dimensional, that plane would map onto this plane. And really all I need to know where you go is the projection onto the row space. Anything you can give me is a dimension in the row space, it's a direction in the row space, and then a direction in the null space. And that direction of the null space you give me in my vector doesn't matter one bit, it's just going to go to 0. So the row space in this case would be some 2-dimensional plane in R2, and that plane maps onto this plane. The output. Do I have any restrictions? Do I have any restrictions on what I could? Well, it says no restrictions there. So, do I have any restrictions? No. Turn it on the board. Like, can I put any numbers in here to make this multiplication? Yeah. Anything in R4 I can put here. That's great. Do I have any restrictions over here on where I can get in R2? In this particular example, no. But depending on my matrix over here, I might not be able to get to R2. If it was rank 1, I would just get a line. If it was rank 0, I would just get 0 over here. The column space tells us where we can end up. Yes.
Okay, so sorry, you answered my question. The column space determines where we can end up.
That's right. So, so anything that we, anything in our input, we can think about as a portion of the row space and then a portion of the null space. That's what this XR plus XN is. But XN actually doesn't matter because A times XN is going to go to 0. So AX equals B. The column space tells me where I can end up in this case, 2-dimensional space, whatever dimension space. Everything else goes to 0. And this null space of A transpose, that tells me where in R2, where that output space is that I can never reach by a matrix multiplication, no matter what vector you do. So, okay, we'll come back to some of this. So, because the read needed for this one really focuses on column space and the row space of A. So what's column space? Well, the column space of A is all linear combinations of the columns of the matrix. We've already done stuff like this. We've done linear combinations of the columns of the matrix. This is our peanut butter and bread example. Here we've got fat, here we've got protein, all linear combinations. Well, what do I end up with? Well, how much of peanut butter and how much of bread? And I get fat and protein. So what's my column space telling me? It's my fat and it's where I end up in my fat and protein world. So in this case, if this was rank 2, then I can get any value in the protein and fat range. There's some combination of peanut butter and bread servings that I can get in R2. Right vector multiplication is a way of representing the column space because this matrix times xy is x of this column plus y of that column. And the column space of A is a set of all protein, in this case, the set of all protein and fat combinations that can be created by different combinations of peanut butter and bread servings. Okay, so it's our output. When we do this multiplication, the column space says something about our output. we multiply that out. If you look at the units, you're going to end up with grams of fat and grams of protein. So we're dealing with a protein fat space. If you want to know, is a certain vector B in the column space of A? Well, that's actually probably we've already been able to answer in other ways. You can think of it as a system of equations, or you can augment and row reduce. And so then that'll answer that question. If you want to describe the column space of A, so we already know the column space is either the point 0, a line through the origin, a plane through the origin, a hyperplane through the origin. If you want to describe that, then you set up your matrix augmented with an arbitrary xy, and then you can row reduce and solve. We did an example like that in the video. And then you can build it, you'll get an equation, which possibly too. I'm just gonna skip that, sorry. Row space. We don't go back to this guy. The spaces we care most about are column spaces and null spaces. It seems like, why would you care about the null space of a matrix if that's just all the vectors that go to the 0? It turns out one of the most important subspaces we study are called eigenspaces, and they turn out to be null spaces of a certain matrix that we create. And so we're going to be creating null spaces almost more than anything else. And column spaces tell us about our output and help us to know whether solutions exist or not. You know, did you give me a beta that's actually in the column space, or did you give me a beta that's not in the column space, so it lives over here? So column space and null space we work the most with. Row space, not so much. And we've got an example here about why. The row space is the span of the rows of a matrix. So all linear combinations of the rows. So that's like, okay, if I take 2 of these plus 5 of these, what do I get? So that's the row space. That's different than if I take 2 of these and 5 of these, that's the column. In a context, matrices often have one space that's easier to interpret, and that's usually the one that gets put as the column space. I can think about this matrix, or I can think about its transpose, and it's going to change. My fat and protein would be here, and then my peanut butter and bread would be my rows instead of my columns. So you can transpose it so it works as the work you want it to do. So what's the meaning of row space in the peanut butter bread fat protein matrix? We already talked about the column space. Column space, if I take some of this and some of this, I'm going to get how much fat and how much protein I have. Think about what is the row space, and then share with your neighbor. Okay, so if I take some of this plus some of this, that's what this is supposed to represent. X amount of 15, 1.5, Y amount of 8.3. If I add that together, I'm going to get something. What am I getting? So think about that and share with the neighbor.
Everything in my physics class is tossing like a total. Right. Well, I can conclude, even though I know better, because I watched the video and know that this is a viable thing.
Hey, anyone have an idea here?
5 or 6 now. When I was walking over here, I still have.
That was nice. That was easy to think about. Why is that harder to think about? Someone answer that question.
Because in this physical context, the quantities you're now trying to manipulate directly are the fat and the protein as opposed to the amount of peanut butter and bread, and that's very weird.
Yeah, they get like, oh, I have X amount, let's say two 15s, which is, would be grams of fat per serving, and 3/8, or yeah, 3/8, which is grams of protein per serving, and I'm adding those together. So I have grams of fat per serving, grams of protein per serving. I could say like grams of stuff per serving. It's like something's not working very well right here. So, yeah, it doesn't work out nicely with this one particular thing. We can't, if we can take the transpose of this, we could think about this in a way where it does make sense. Still, with the row space that makes sense. We could, instead of doing 15, 1.583 XY. So this is going to be, we're going to get fat and protein out this way. I could think of it this way. Y XY 15, 1.583. So what did I just do? I did the transpose. In fact, I did the transpose of like this and the transpose of this. So I'm just going to transpose both sides. So I get the transpose of XY times the transpose of this. And here I end up with a row matrix, with a row vector. And it has the same meaning as I did over here. It's just transpose. So I'm going to get fat and protein. Okay, so here the row space is the same as the column space of the transpose. So we could, this is easier to think about because this is exactly the same thinking that we had with the column space. So row spaces can make sense. This just makes a lot more sense with the matrix times the vector in a lot of situations. Then when you think about this is doing some transformations on this vector. So is a certain vector B in the row space of A? Well, how do you answer that question? Well, one thing you can do is you can augment and row reduce, except you don't augment it with A, you augment it with A transpose. So the question is 1, 2, is that in the row space of 15, 8, what is this one, 1.53? Is this in the row space of this? Well, I don't know, but I can transpose that to be 15, 1.583. That's back to, oops. And then transpose my 1, 2, and then I can row reduce. Because the combinations of these to get this, that's what I really want to know. How much of this plus how much of this do I need to get these? Or even is it possible to do that? Well, that's the same as how much of this and how much of this do I need to get this because they're transposed. Or you can augment and row reduce where you put the row vector, you augmented it down here, and then you row reduce. And if you get that bottom row to be zeros, then it is in the row space because you just did linear combinations with the rows to cancel that last one out. So it must be in. So, okay. All right, let's get back up to these. We won't go through all these, but whole numbers, are they closed under addition? Yeah, any two whole numbers I add together, I get another whole number. Are they closed under subtraction? No. 1 minus 3, I get a -2. That's not in there. Okay, so if I want something closed under subtraction, I could jump to the integers. The integer, are they closed under addition?
Yes, sir.
Are they closed under subtraction?
Yes, sir.
Are they closed under multiplication?
Yes, sir.
Yeah, if the whole numbers are integers, they're both closed under multiplication. Are they closed under division? No. If I want something that's, so now I have to, this is closed under multiplication and addition. This is closed under, the integers are closed under multiplication, addition, and subtraction. If I want something closed under multiplication, subtraction, all four things, I have to go to the rational numbers. All the rational numbers are actually closed, they're closed under division. Two rational numbers, one rational number divided by another rational number, they're closed.
Rational numbers equal 0.
Yep.
So what if it's less
So P, yeah, Q, this should say Q not equal to 0.
than 0?
Sorry. Yeah, so we should specify, this is any rational number, or any integer that's 0. So same thing came up last class. Is that what you're gonna say?
Did you say whole numbers were closed under powers?
Nope. So, but they probably are, like,
Yeah, they are.
yeah,
they would
so
be,
if we take a whole number to a whole number,
But weirdly, integers are not closed under powers.
right, integers are not close. The real numbers, so yeah, when we get into the powers, we end up with like the square root of 2. That's not a rational number. So you need to add others to make sure that you're closed under powers, at least powers of positive ones, and then
Yeah, so real
add
numbers,
all powers. You have to add the complex numbers. And the complex numbers are closed under all of these.
so real numbers still aren't closed under powers.
So real numbers, that's right. There might be a certain way to restrict it to say what power it is. It is closed under. But complex numbers, we don't have to add on anything else. So the complex numbers are closed under all algebraic operations. So, okay. So we have enough time to do this. Let K be the set of all vectors V and R3 of this form. The question is K a subspace, and why or why not? So I've got vectors here in V where y equals x and z equals x cubed. Okay, so these have to be the same value, and z has to be the cube of this one. So someone give me one vector, one non-zero vector that's in there.
1, 1, 1.
1, 1, 1. Okay, that one's in there. How about a more interesting one?
2, 2, 8.
Just to make sure. So 2, 2, 8. Okay, so 2, 2, 8 is in there. So is this a subspace? You get to check to see if all three of those things are in there. And then you get to show that the set of vectors in the line y equals a negative 3x is a subspace. How would I represent the vectors on that line? It's not right. Hold on. I'm doing it. Yeah, so all the vectors of that form are the vectors on the line y equals a negative 3. Okay, so here you have to show that all three of those things, all three of the criteria are satisfied with these vectors. Okay, so I'm going to turn it loose. Your turn. Go ahead. You can work with a neighbor as you do these things. So go ahead.
The first one.
And I are here.
Wait.
Set that up. Pretty sure you can get second or fourth quadrant.
And I was like kind of there's just two numbers, x, z. Or x, cubed.
Get positives and negatives in this one.
Is that a
Positives or negatives.
It seems, yeah, that's where I'm from. Negative or highly restricted, isn't it? Yeah, if you can write it in the equation.
Therefore, K is.
Because it would just be everything along the like I I think still wouldn't be a plane, would it? There would just be a line bent in the z direction. Either below x cubed. So it's like, or given a from the top side, y equals x cubed. Do you think about that? But instead you're taking it from the side. So if you look at it from the top, it would be y equals x cubed. If you look at it from the side, it's
The second one.
how y equals x. So it's like taking.
I can guess myself.
Down.
I'm just trying to.
Pull it up to here, and then you tilt them. Still only that one small line. Is it a subspace? I doubt it.
It spans getting this
Any
in.
number of things you can calculate. Adding.
Okay to me.
Here, vector 1, 1. And then we take, add it to 8.
I would say shake that on the wall.
It's not a subspace. Feel like I like that way more than whatever frick you were just talking about. I like mine. I think yeah. You like that turn on the side? Look at it from here.
Yeah, two-dimensional spaces still hard to
Really?
I haven't done a lot of modeling. I don't know how to set it up.
I do so much modeling. Not more force of the vectors than what you do in my React. Why, yes.
I mean, one of those.
Through the origin, it's closed under 4 hours here, and it's closed under the other one. To show that. We're pretty gay to make this.
You can pull this down in a minute. Take a picture if you want.
It's a screen protector.
Closed under multiplication. Three times 2x, but it's still on the line. It's like a proof with scalar multiplication. Going backwards from multiplication. I feel like I should do the other way around, but I don't use it because I'm doing it in my head. Oh, and it obviously goes through 0 because it does.
So when x is 0, it's 0. This is huge.
Classic move.
Because I couldn't for the addition.
All right. What do we think about this first one? Is K a subspace or not? So thumbs up if you think it's a subspace, thumbs down if you think it's not a subspace, thumbs sideways if you have no idea. Okay. We see lots of downs, a couple ups. Okay,
Yeah.
so it's not a subspace. The question is why? So why wouldn't this not be a subspace?
Explain this piece.
So I'm gonna have a counter example. Easiest way to show that something's not a subspace is to find a counter example. Yes.
Build the addition with the 111 plus 228. 9 is not 3B.
Nice. Okay, so both of these are in.
That's how I do it.
I always have trouble with this. Okay, there you go. So these are both in K. So those are both vectors that live in K, right? They're of the form x cubed, but this is not something, because I'd have to have, if x is 3, then that would have to be x, that would have to be 3, 327. That's enough to show, hey, this can't be a subspace. I found two vectors added together that don't fit that same path. So can't be a subspace. Yes.
Can you show how to do it like generally without using any specific numbers?
So if you're doing counter examples, specifics are great. They're easier. So but on the other problem about show the set of vectors on the line y equals -3x to the subspace, then you need to be general. So
Like on a homework, if you're asked to prove or disprove something and it's not true, just give a counter example. But if it is true, then you have to show it more generally.
So here's it. It's also not closed under scalar multiplication. A specific example is 2 times 1, 1, 1. That's the vector 2, 2, 2. But that's not. If that's at x equals 2, then I have to end up with this vector, and I don't. So it's not closed under scalar multiplication. So not a subspace. But now for the other one, I'm going to show that that is a subspace. I have to show any vector or any set of vectors. If I'm doing addition, I have to show any two vectors in there. If I add together, has to be of that form, has to be on that one. And if I have any vector and I multiply it by any real number, it has to be on that one. So how do you do that? Well, I'm not going to pick specific numbers. I'm going to keep it as things like x and a negative 3x. So what if I multiply that by c? Well, first, is 0 in there? I should check. So number 1. Okay. 1 is the 0 vector part of this on the line y equals a negative 3x. Yep, because at x equals 0, you get 0, 0. So check. It is 0, negative 3, 0. Check. So how about closed under scalar multiplication? So if x equals a negative 3x is c times a negative x and negative 3x, is that of the same form, or does that fit the same line? Is that on there? Well, let's do the algebra. We're just doing properties of our scalar multiplication here, and that's going to be c x. Factor out that negative 3 and write it this way. Which, and then I could let, it's like k equals cx or something, and I get k negative 3k, so it's of the same form. So whatever my x coordinate is, my y coordinate is a negative 3 times that. So check. How about, we have 1 more minute, and I'll let you guys do this. Just think for 20 seconds. How would you do the addition one? I'll do it in a second. How would you show this last piece? With any two vectors on that line I add together, I'm still on that line.
CX plus
How can I write any two vectors? So when you get to the addition part, it's really nice to use like x1s and x2s. So you can write, you can do a scalar thing. I think this is a little bit easier. So I'm going to pick x1 and a negative 3x1, that's one vector. And x2 and a negative 3x2, that's any other vector on the line, right? The vectors of that form. So I add them together, and what do I get? I get this. Question is that still, is that of that same form?
You can factor out the negative 3.
Yeah.
yeah. And then x1 plus x2, we can call a new variable, and therefore it is of that form.
That's right. You want k equal x1 plus x2. Then I still get k negative 3k. Let's close under addition. So there's an example to show. Check all three of them. So these are the kind of proofs that might end up on an exam. Okay, but they're going to be pretty straightforward. Exactly what you need to show, you'll have to practice and do them. You won't be having to create up a proof line. Have a great day.
Yeah. In the time.